So the chi-square independence test. So on your calculator, if you go into the test menu, it's called chi-square test. So our first step here normally would be to define a parameter. In this case, there will not be one. So we're going to state the null and alternative hypotheses and the level of significance. So in this case, there's no parameter here. Our null and alternative hypotheses are completely all in words. So this is going to be whatever the row variable is and whatever the column variable is. And the null hypothesis is always going to say that they're independent. And then the alternative, same row and column variable, but now the alternative will say that they're dependent. And again, we're going to still state our level of alpha level here, level of significance. Next step is to check the assumptions for the test. In this case, again, we still have this underlying assumption that a random sample has been taken. And so this one, we need the expected frequency for each cell to be at least 5. And these are the expected ones, not the observed ones. So these are the ones that actually need to be computed, assuming the row and the column variable are independent. So now when we run this chi-square test, we are going to check those values in matrix B after we run the test. So it seems a little weird. We're going to actually check the assumption after we do the test, but it just makes it easier to make all those computations to run the test and then go back and check and see if the conditions were met. And again, the third condition here, again, cap n is at least 20 times little n, and again, we're just going to assume that's true if cap n's not given. So in this case, the test that we're going to be using is going to be the chi-square independence test. So our test statistic, we've got, again, two forms of technology to use here. So whether we're using the calculator, we would first need to enter a matrix of data. Okay, so not a list of data, but a matrix of data. So we would go into second X inverse to get into the matrix feature of the calculator and arrow over twice to get to the edit menu. And we would push 1 for matrix A. And then you need to tell it how many rows and how many columns you need, and then enter the data in the matrix exactly how it looks in the contingency table. And we're going to see that in an example here in just a second. After you've entered the data into a matrix, and we're going to go into Stat and arrow over to the Test menu and scroll down to find the chi-square test and highlight next to that and push Enter. And then on your screen, these are the defaults, and so as long as you've put your observed data in matrix A, this tells us it's going to put the expected counts in matrix B, and then we can hit Calculate. And on the output screen, we have, again, our chi-square test statistic. And again, where it says P, that's not really P, that is the p-value. And again, it says 8.58, but we know that a p-value cannot be 8.58 because the p stands for probability, so we need to make sure we check the end of the line, and we see that that's really times 10 to the negative 4. So we have a really tiny p-value there. So once you run the test to see the expected matrix, we need to see the values that it's stored in matrix B. Those are the values where it would have taken the row total times the column total and dividing by the sample size, the formula that we developed on the first page of this set. So we would push second function X inverse again to get into the matrix, and we would push button 2 to choose matrix B and then push Enter. And we'll see here in a second how we will see all those values. Now in StatCrunch, we would first need to enter a contingency table like we did in Chapter 2, and these are a bit weird to enter into StatCrunch. So I've put here just kind of some generic categories and titles. Now your contingency table might have more categories. This one just has 2. But in this case, we put actually the name of the top of the row here, the name of one of the variables, and then all of its categories. But then the other column names are just going to be all the other categories for the other variable. And then we put all the cell counts in between here. Okay, once you've entered that, we would choose Stat Tables Contingency with Summary. Under Select Columns, you would choose all the columns except the first one. And then under Row Labels is where we would choose the first column. And then under Display, you should choose Expected Count so that we can see those, so we can check the condition for the test that they're all at least 5. And then you click Compute. Okay, so no matter which technology is being used, this is the formula that it's using for that value of chi-square. Okay. Our next step is to obtain the p-value, which is going to be on that output screen, and then to illustrate the meaning of that p-value. So again, the p-value is this tail area. And for these tests, these are always right-tailed tests. As we're taking each of those observed minus expected and squaring it and dividing by an expected value, and we keep adding that on for each cell. Okay, in theory, if the expected values match perfectly to the observed ones, that whole sum would be 0. And for each of the differences between the observed and expected values, this adds on a little bit more and a little bit more and a little bit more. So we keep moving to the right of 0. Okay, so there is no moving to the left or moving to the right of some central value like we had with z-tests and t-tests. All right, then we go to make a decision, which is the same as we've had before. If the p-value is less than or equal to alpha, then we fail to reject. Say what? No. Reject HO if the p-value is less than or equal to alpha, and we're going to fail to reject if the p-value is greater than alpha. So again, as we get further and further away from 0, that means the observed and expected values are getting further and further apart from each other. And as we get further away from 0, the tail area gets smaller to the point where it gets small enough. And if it gets to be less than or equal to alpha, we don't think those, the row variable and the column variable, are independent, and so we reject that. And our conclusion's still the same. If we reject HO, that means there is significant evidence to conclude. And again, we put HA here in the context of the problem. And if we fail to, then there's not.